Okay, here is another kind of inelastic collisional process. Okay, and it's named photoionization. Photoionization. Okay, so in a plasma state, we can also use photons to ionize the gas, and this process is named the photoionization process. So again, we take argon as the example. Argon as example. So the ionization energy of argon is 15.5 electron volt. 15.5 electron volt. So if we use light to irradiate the plasma or irradiate a gas, and if you can change the energy of photon, you can take this experiment. So you might use a xenon lamp as the light source, and let the light pass through a monochromator, so that you can choose certain wavelengths of light to irradiate the gas, and then find out the ratio of the ionization. So the gas atom, so the argon atom become ions because the photons interact with the argon atom. Okay, so maybe you can write an equation. The photons, right? Maybe you can write a simple equation. Photon, usually we use H mu to represent the photon. Okay, so when the photons collide with argon atom, you generate electron and ion pair. So you can write this kind of equation to represent the photoionization. Okay, and the horizontal axis shows the energy of photon, right here from 10 electron volt to 30 electron volt. So if the energy of photon is less than 15.5 electron volt, and then the cross-section or the probability of photoionization is 0, the probability. And if the energy of photons is higher than 15.5 electron volt, and then we can see here is a jump, abrupt jump of the cross-section or the probability of the photoionization. Okay, and sometimes we use wavelengths, the wave behavior to describe the photons, the light. Okay, so light can be described by the wave behavior or particle behavior. So if we describe the light by the particle behavior, we can count the light as the photons, right? Photons with different energies. And if we consider the wave behavior of light, we can use the wavelengths, and wavelengths and the energy of photons, can be converted. Okay, so in this case, for a photon with energy around 15.5 eV, around here, the wavelength is around 800 angstrom. or 80 nanometer. So 80 nanometer is extreme UV light with very short energy, very short wavelength and very high energy UV light. Okay, so you need an extreme UV to ionize argon gas. Extreme UV. So this is another inelastic conditional process. So it is known as photoionization. So this is another way, or you can use this to generate plasma. So in the plasma fusion reactor, people also use laser beam with very high energy, very high photon energy to ionize hydrogen gas. So you can use laser beam, but you need a laser beam with very short wavelength. So it belongs to the extreme UV wavelength. Okay, and here is another important inelastic collisional process. So it's named as excitation. So if we look at the figure here, so again, here is a primary electron with high energy, right? Energetic primary electron. When an electron collides with a gas atom, a neutral gas atom, the collision might bring the electrons from ground state, low energy ground state, to higher orbital or higher energy state. So if we look at the model of the hydrogen atom, right? So hydrogen is made of one proton. The nucleus is proton, and then surrounded by one electron. But the electron can be at different orbital. And the first one is n equals to 1, right? The principal quantum number equals to 1. So this is the most inner orbital surrounding the nucleus or surrounding the proton, n equals to 1, the principal quantum number. And then this is n equals to 2, the principal quantum number equals to 3, 4, and to infinity. Okay. So there are different orbitals for the electron. So the lowest orbital is n equal to 1. Okay. And you can also another symbol to realize the energy of electrons of the hydrogen atoms. So n equals to 1, also known as 1s, right? N equals to 2, 2s, 2p. 2s, 2p orbital, right? And n equal to 3, 3s, 3p, 3d. So there are different orbitals. Okay. 1, 2, 3 is the principal quantum number. Okay. So if you ionize hydrogen atom, it means you let the electrons of the hydrogen atom release so that electron become free. How can electron become free? Because the electron gain an energy equals to the ionization energy of hydrogen atom. And the ionization energy of hydrogen atom is 13.6 eV. 13.6 eV. So if you apply if you use an electron impact, right? The primary electron, the energy of primary electron is higher than 13.6 eV. Then during a collisional process, right, the electron surrounding the hydrogen, surrounding the proton, can get the energy higher than ionization energy and then escape and become free, can travel free inside the plasma, And such process is named the ionization process. But if the energy of the impact electron or energy of primary electron is not that high, right? It's not that high. It's smaller than 13.6 eV. The collision might bring the electron from n equals to 1 orbital to a higher orbital, right? So in this figure, the electrons jump to a higher orbital, but the hydrogen atom remain as a neutral state, so that the charge, net charge is still zero, but the electron has higher energy, and such kind of the hydrogen atom is called metastable or radical, state or high energy state. And this process is named excitation or electron impact excitation. So the process bring the electrons from lower orbital to higher orbital, but the electrons still attracted by the nucleus, okay? And this metastable state or radicals are also very important in plasma process. Okay, later on we can see the metastable state also contributes to the generation and the sustaining of plasma by another collisional process also, okay? And also the metastable states are highly reactive. So one can use these radicals to run chemical process. So basically in plasma enhanced chemical vapor deposition, one needs to generate a high concentration of metastable state, to undergo chemical reactions. Okay. And in a sputtering system, one needs to create high concentration of ions. So they are different process. Okay. And inside the plasma, inside plasma, there are different particles, right? So for example, if you use hydrogen gas to create a plasma, so you got hydrogen molecule, okay? And then hydrogen atom, and with high energy condition, so we can place a steric or a star over here. So this represents radical or metastable state. Okay, so both the molecule or this metastable states are electrically neutral. Okay, and they are cations, they are electrons, and the hydrogen molecule can also be ionized. So here is the H2, and then with one positive charge. So there are different species. So one can use the radical to promote chemical reaction, and one can use ions and use electrical field to accelerate ions, and then cause the ion bombardment with a solid surface. Solid surface. So that's an application of plasmas. Okay, so this figure shows electron impact excitation. Okay, and you can also use photons to cause the excitation process. So the process is named photoexcitation. Photoexcitation. And if you can bring your plasma to a very high temperature condition, you can also use thermal energy to generate excitation state or metastable state. And such process is named thermal excitation. Thermal excitation, okay. And the lower right figure shows the cross-section or the probability of the electron impact ionization. So the horizontal axis is the energy of primary electron. Energy of primary electron. And the vertical axis is the cross-section of the electron impact excitation process. So they are different orbitals, right? For the hydrogen atom, there are different orbitals. So you can undergo the 1s to 2s. So that you can excite the electron from 1s orbital to a 2s orbital, or from 1s to 3p, right? The n equal to 3, there are 3s, 3p, and 3d. Okay, so they are different orbitals. You can also excite the electron to 2p orbital. So for each excitation process, the curve for the cross-section for the electron impact excitations are different. So they are different curves. On all these solid curves is based on the calculation, and the curve with the dash here is from experiment. Okay. Okay, and in this figure, right, if we excited electrons from the lower orbital to higher orbital, we can draw the path. So, for example, from 1s to 2p, okay, 1s to 2p, you can draw the curve 1s to 2p. This is the excitation curve, excitation process, okay. And then later on, the excitation state may not exist for a long time. Okay, so later on, the electrons might fall back from high energy state to low energy state, or from excited state to ground state. Right? But there's a difference of energy between excited state and ground state. So during this process, right? During this process, the energy will be released by emitting photons. And this is the major part of the luminance in plasma. The luminance, right? Once we generate plasma, we can see a light irradiate out. So the light, most of the light we can see coming from this process. Okay. And based on this process, you can calculate the energy difference between different energy levels or different states. So, for example, if the electrons fall back from n equals to 3 orbital to n equals to 2 orbital, the energy difference might convert into photons. And the energy of the photon or the wavelength of the photon can be calculated, right, based on this quantum theory. So the light emission emit out with a wavelength of 656.3 nanometer. And this is a red color. Okay. So when you generate plasma, you always see a red or pink color of the light emission. It is caused by the energy transition between n equal to 3 and n equals to 2. And if the electrons fall back from higher level to the ground state, for example, from n equals to 2 to n equals to 1, the difference of energy, right, also causes the emission of photon. And the energy of photons can be very high, like here, 121.6 nanometer. So this part belongs to the deep UV. So once you generate plasma, you can generate light with different wavelengths. And the wavelengths of these lights, or these photons, are the characteristic of atom. So when you generate hydrogen plasma, you can see the color of this light. And when you generate argon plasma, the color looks different. And if you use a spectrometer, you can record the spectrum of the plasma emission. Okay. So in this course, we have two lab 2. So in one lab 2, I will ask my student to generate plasma and let you record the plasma spectrum. Okay. So it's in this slide. Okay. So this slide describes the phenomena I just introduced. So once the electrons are excited to a higher level or to an excited state, there are chance for the electrons to fall back. So when the electron fall back from high energy level to a lower, higher orbital to lower orbital, the energy difference will convert it to light. So the energy difference delta E equals to the light energy h mu. We always use h mu to represent the photons. So this light emission causes plasma to glow. So plasma, also named as ionized gas, right? Electrical discharge and glow discharge. Okay, and the glow coming from this process, and this process can be named as relaxation process or de-excitation process. Okay. And from the last slide, we have already seen that for the hydrogen plasma, right? Hydrogen plasma emit light with certain wavelengths. And for argon plasma, for oxygen or nitrogen plasma, they also emit light with specific wavelengths. So you can use an optical spectrometer to record the light emission from plasma. And in industry, people use the carbon tetrafluoride gas and the oxygen gas, and then generate plasma. Use this plasma to etch silicon oxide and etch silicon. So they need to monitor their plasma condition by using the optical emission spectrometer. Optical emission. So in this spectrometer, you can take the spectrum from plasma, and then you can see the plasma emit light with certain wavelengths. And the oxygen plasma generate light with the wavelengths in this region, and fluorine generate light with this region, and others N2 CO. Okay, so you can take the spectrum easily. And for the wavelengths between, in the range between 400 nanometer to 700 nanometer, so this region belongs to visible light. Visible light. So you can see the light emitting out. But if the wavelength is longer than 700 nanometer, this part belongs to infrared. So you cannot see infrared. But you can use the machine spectrometer to record the infrared. Right. And for this part, if the wavelength is shorter than 400 nanometer, this part belongs to UV light, okay? UVA, UVB, and this part is UVC, okay? And UVB and UVC are dangerous to our skin and to our eyes, okay? So if you have a plasma system, don't just look at the plasma through the window. You need to wear a glass goggle with the UV protection. So you must cut off the UV light. So you need a special goggle when you run this experiment and when you look at the plasma. Okay. Yeah. So in this figure, right, I took a picture of the plasma from a slit window in my lab. Okay. So the color is pink color. I create a hydrogen plasma, pink color. Okay. Yeah. Okay. So this table shows the color of plasma. Right? So if you use hydrogen to create plasma, you can see a basically pink color in positive column. Positive column. Okay. So in the chapter of glow discharge, you will know there are several regions of plasma. If you generate plasma between two electrodes, so there are cathode region, a negative glow and positive columns. Okay, and if the gas pressure is higher than minitor, if it is 10 minitor or 100 minitor, the cathode region and negative glow are very thin. So you will always see a positive column. Positive column, okay? So for hydrogen plasma, the positive column is pink. Nitrogen, the positive column is red. And oxygen has a complex color, the pale yellows with pink center. Okay, dark red, okay, different color. And if you generate a titanium plasma looks like a little bit green, blue to green color. So all these colors are the characteristic of this gas. Characteristic of this gas, okay. And in the glow in the discharge chapter, you will know the first cathode region negative glow, positive column, and the anode region. They are different regions. So in Chapman's books, he also shows different conditional process. Okay, so I just pick up a few conditional process to introduce. Okay, recombination. For the recombination, the process will cause fuse the ions with electron. Recombination process. Right? When we run the ionization process, electrons was knocked out from atom to create electron and ion pair. If the electron and ion meet together, they will recombine and lose their charges. This process is called recombination. Okay. And this one is the dissociation. Dissociation. So if you learn the chemical process, you can tell dissociation and ionization, they are different. They are different, okay? So in the dissociation process, you start with a multiple atom atomic molecule, and then cut the molecule into several species. So for example, if you start with oxygen molecule, oxygen is diatomic molecule, right? Two oxygen atoms bind together to form oxygen molecule. And the dissociation process will produce two oxygen atoms. So the oxygen molecule, one oxygen molecule, become two oxygen atoms. Two atoms. This process is named dissociation. And for this dissociation process, oxygen molecule is neutral. Oxygen atoms are also neutral. Okay. So when the electron collide with oxygen molecule, it might undergo this kind of reaction. There's no charge transfer, but the oxygen molecule was split into two oxygen atoms. Okay. And as I mentioned earlier, right, these radicals are highly reactive. So that once you create the oxygen radicals, they can react with organic compounds. Okay. And if you start with a carbon tetrafluoride molecule, and you can dissociate this molecule into two radicals, CF3 and F radical, fluorine radical. So in industry, people use fluorine radical to etch silicon. So you can run plasma etching process. H silicon, use fluorine. So this process is also the dissociation process. Dissociation, so that you create CF3 and F, right? Okay. So for example, if you mix CF4 with oxygen and generate plasma, you got fluorine in the plasma phase, fluorine radicals, right? So the emission of the fluorine, photo emission of fluorine for in this place. And you got oxygen radicals, right? For in this place. Okay, and this process is named electron attachment. So from this equation, you can see when an electron collides with an SF6 molecule, the electron might just attach to this molecule. Right? So the molecule becomes SF6 and with one negative charge. So this process is attachment. Okay, and there are ion neutral collision and metastable collision. So in the next slide, I will explain the metastable collision. Okay, because this collisional process is also important because they can generate electron and ion pairs. Okay, so some excited atoms or some metastable states, right? They might exist for a long lifetime. So for example, fluorine radical can exist for a very long time. Okay. So since they exist for a long time, so they might get an collisional process again. So for example, in this place, a metastable species can collide with a neutral species and cause the ionization. So in this equation, the A, right, with the start here is the metastable species. Maybe argon radicals or hydrogen radicals. Okay. So when these radicals meet an atom, gas atom, and this gas atom at the beginning is at ground state. So here use G to represent neutral atoms at ground state. Okay, and since the radicals might have high energy, for example, the argon radical or argon metastables can have an energy of 11.55 eV or 11.7 eV. They can have such high energy because when we generate argon radicals, we need to bring the electron, right? Electrons of the argon atoms from low energy level to high energy level. So the argon atoms in the excited state has an energy higher than the argon atoms at ground state. Okay, and the energy is the excitation energy. The energy is the excitation energy. So if we take a look at the hydrogen atoms, ground state, right, energy of electron at the ground state is the base, okay? And if we can excite electron to n equals to 4 orbital, you increase the energy of hydrogen atom from 0 to 12.6 eV. So for hydrogen radicals, this hydrogen radicals has an energy of 12.6 eV. And for the argon gas, the radicals of argon can have energy around of 11.55 or 11.7 EV, 7 EV. So such high energy of radicals may, when they collide with a neutral species, they might, ionize the species, neutral species. And for neon has higher ionization energy than argon, and also have radicals with higher energies. So for example, neon has energy, radicals have energy of 16.6 or 16.7 eV, right? So if a neon radical collide with argon atom, the energy is higher than 15.76 eV. So the neon radical can ionize argon atom. Okay. So such process is called metastable and neutral collisions, or named as Penning ionization. Okay. So this example can be written as neon radical collide with argon atom at ground state, and then cause the ionization of argon atom. So the product is argon ion and electron. And the neon radicals become neon at ground state. So this is a Penning ionization process. Right? Because neon radicals have energy higher than the energy of ionization of argon gas. Okay. And the second equation here is metastable ionization. So when two argon radicals collide with each other, they might cause the ionization of one argon atom. Okay, because the argon radicals have energy of 11.55 or 11.7 EV, right? So, and the ionization energy of argon is 15.7 EV. So if you want to ionize the radicals, you only need a small amount of energy. So for example, only need 4.21 EV to ionize an argon radical. Okay. So this process, metastable and metastable ionization process, will produce an argon ion and electron pairs, and one of the argon radical fall back to the ground state. Okay, metastable ionization, and the final one is the electron and metastable ionization. Okay, so if an electron collide with an argon radicals, and if the electron energy is a little bit higher than 4.21 EV, right? If you add 4.21 here, 4.21 to 11.55, right? If you add them together, the value is larger than 15.76 EV. So this process can also cause ionization. Okay. So here are the collisional process in plasma. So once the collisional process produce electron and ion pair, the process can contribute to the generation of plasma and sustaining of plasma. So all these processes are important in plasma generation and sustaining the plasma. Okay, but it requires two steps of collisional process. So the probability of this process is much smaller than the probability of the previous single step collisional process, because it requires two steps. First step is excitation, right? Excitation of neon. This is first step. And then the second step, neon and argon collide. So you need two steps to undergo this process. Or in this process, the first step, you need to create argon radical, right? By electron impact excitation. And then electron impact metastable ionization, two steps. So the probabilities are low for this metastable collisional process. Because here are two tables. Okay. So the left table shows the chemical bonds, CH, CN, okay, all these chemical bonds. So in chemistry, we can find out the chemical bond and the energy of chemical bonds, but they are always represented by the kilocalorie per mole or kilojoule per mole. But in this class, we have already known that the unit can be converted to electron volt. So right here, the energy of these chemical bonds shows here in electron volt unit. And in plasma, there are different species. So the energy of this species can be in this range. So if you compare the energies of the species in electron and energy of chemical bonds, so we can estimate if this species meet with chemicals, whether this species can break the chemical bonds or not. If the energy is high enough, they can break these chemical bonds. Okay. And in this table, here are the molecules, oxygen molecules, nitrogen molecules. So the excitation of oxygen molecules require 7.9 eV, and ionization requires 12.5 eV for oxygen molecule. And for oxygen atom, the excitation energy is 1.97 and 9.15, and ionization is 13.6. So you can also compare the excitation energy and ionization energy of these molecules with the energies of this species in plasma. Okay, so any questions?